Okay, good morning, everybody. We're back to only 50 minutes of suffering today. Like I normally do in a regular classroom, I take care of business first. Um, next Tuesday, next Tuesday during our regular class time, I'm gonna do the review for the exam. So make sure that you are on time next Tuesday. I'm gonna do the review for the exam. Christian is the one that recorded the lecture. Yesterday, he did the recording, but no sound at all. So if anybody in the class has recorded the lecture yesterday with sound, please send it to me. Um, Also, I tried yesterday and creating for the exam, I'm creating a folder. And inside the folder, there are going to be 3 questions. And you're going to have 1 hour to solve the problems and upload them. I'm going to give you more information, but I'm just practicing on that. Any question before I start lecturing? Any question at all? Yeah, 1 hour each pro. I'm gonna design the exam for you to be able to solve it in less than 1 hour. You can check it and upload it. What a pro, I'm gonna require that if everybody had the cameras on so I can look at your faces. I really miss you. Any other question? Oh, we're gonna try to start at 7 o'clock. 7 to 8, 8 to 9, and 9 to 10. And obviously, I'm going to give you a bonus. Uh, I looked this morning for exam number 1. I couldn't find it at home. So I'm going to go to UTSA probably this weekend. I just need to check with the administration. So I can go to my office and get the exam if the exam is in my office. But I'll let you know if I find it. I'm still looking for the exam. What do we do if we don't on the camera? Don't worry. I'm gonna miss your face. Any other, any other question? Okay. So let's start. Look, yesterday there was a question about the torsional backlink, especially about the K, this KZ. The K is the same K that we use for the cone. So this is, in the case of pin is 1, in the case of fix and pin is point A, and this is the length, the axial length of the member. So in this case, this is from this point to this point is L. This is an example of the torsion. So I want you to pay attention. I did go over this stress diagram yesterday. And this is a typical cross section. If you had gone to the field, most of the time we use a Y flange. And the reason why we use a Y flange is obvious because it had a large moment of inertia about the x-axis because there's a large concentration of area. The flanges, they have a large concentration of area, so area distance square is going to be a large value. So I was practicing before most of you came about the bending. So when you start this cross section, it's straight. And when you apply load, it bend. So what we had in here is a different situation, bending due to small load. The whole cross section remain elastic. That's why here they say that the moment is smaller than the elastic moment, and the top fiber and the bottom fiber, they have not yielded. They have not got into sigma y or fy. This is a typical case of first yield. The top, because the largest one, the stress becomes fy or sigma y, and because symmetry, the bottom also had that value. So since we had increased the load, remember that plane section before bending remain plane after bending. So this is the rotation of the cross section. More more low, the cross section rotates more. This is the boundary between elastic and inelastic. So if we were to compute the moment of this cross section, remember what I said, T equal to C, and in theory, the force times the distance is M. And here, like I said, there are different areas, so we have different forces, but in theory, it's the force times the distance. This is the very interesting case. Only steel can do that because steel, I showed you yesterday. This is a typical stress strain diagram for steel. We had a linear portion elastic. This is what it yields. It cannot take more load, but it deform until it becomes strong. So in this case, one yield, it cannot take more stress. So the next one will yield. And after that, you keep applying the load, the next one will yield. And the next one, the next one. The same because of symmetry. The same happened with the bottom portion of the beam. So this is a situation where it is semi-plastic. Look, all of this is plastic and all of this is elastic. So this is a typical case where the moment is larger than the moment at first yield, but smaller than the plastic. If you keep applying load, and normally we do this in the testing lab. When you took the course, I know that no longer we do this in the testing lab, but normally in materials course, they use a I-beam, and you can see how it bends and how it tries to get out of the plane. So we're applying so much load, everything in here has yielded. Only steel can do this because it has the same properties in tension and compression. But this is when we have developed the plastic hinge. And this is the plastic hinge, and this is the plastic moment. So for the design of beam, we're going to have the very first portion, we assume that the compression flange is fully supported, or encased in concrete, or closely braced. So we're going to apply a lot of load, and the cross section is going to be able to develop the plastic hinge fully. It's going to be plastic. So there are three situations. So the code, where I stopped yesterday, this is where I stopped yesterday. I told you that the section that can develop the plastic hinge, we call a compact section. So sometimes whenever you do a design, you're gonna assume that the section is compact, and later we're gonna check. This is a typical beam. They put the X to indicate bracing, only brace at the end. So this is the embrace length. L sub B for beams is going to be called the embrace length. And this indicates braces is not an additional support. We still have the same two support. We still have this support here and this support like we did before. So we are not adding a support. We are adding a lateral brace. So now we have L sub B is obviously larger than this value. So this is the critical. And they indicate that this X is that they are supporting the compression flange. I mentioned to you yesterday, the compression flange is like a cone. It's gonna try to back up about the weak axis, but it can't because it's fully supported by the web. So it will back up about the strong axis. But right now, because it is supported, it will not back. I'm gonna show you in the code where you can find this sketch. This is the plastic moment. So there's certain embrace length, certain L sub B from this point to this point, where we're gonna be able to develop the plastic moment. There is a limit in here called L sub P, and there is a limit called L sub R. Between L sub P and L sub R, we had a linear equation. You can see a straight line, and this linear equation means that we're gonna have a moment between the elastic and the plastic moment. So this portion in here is the equation for this condition. Partial plastic, partial elastic. The first condition that I show you is fully plastic. So between this point and this point, fully plastic. In here, between L sub P and L sub R, I'm gonna show you later how to compute L sub P and L sub R. There is a linear relationship. This is partially plastic, partially elastic. Whenever we had a real large embrace length, the behavior is gonna be elastic. And here we had, instead of a straight line, we had a parabola. So in this diagram, this is the condition shown in there. In here, between L sub P and L sub R, for the inelastic, LTB means lateral torsional buckling. Inelastic behavior with lateral torsional buckling. I'm going to show you, I'll tell you what lateral torsional buckling is later. This is elastic, but also lateral torsional buckling. In here, there's no lateral torsional buckling, no instability. So these are the three equations that we're going to see in the book. Also, like we did before, in chapter B, we had a table. This is the way we classified the different shapes. It's going to be as compact, not compact, and slender. In chapter B, I'm going to show you the table when it give you the lambda. Now we had lambda, lambda sub P, and lambda sub R. And these are the conditions. Is lambda, and lambda is B over 2 times the thickness of the flange like we did before. Is lambda is more than P, and the flange has support, and the flange is continually supported to the web, the shape is compact. If lambda is going to be between lambda sub P and lambda sub R, the shape is not compact. And when lambda is larger than lambda sub R, the shape is slender. So we're going to have 3 conditions, and I'm going to show you this later in the code. And these are the equations that on chapter B in the code. The same as before, B over 2 times the thickness of the flange, lambda sub P is this value. Lambda sub R is the same value, but instead of 0.381. And for the web, H over TW, like we have for columns, lambda sub P and lambda sub R. So based on the lambda, this is very similar to the previous sketch. Look. This is the previous one. It had M sub P, M sub R. It had L sub P and L sub R. This one, it had M sub P, but M sub R, you're gonna see that it's called 0.7 FYSX. And instead of the L sub P, it had lambda sub P of the flange, and it had lambda sub R of the flange. But this is the same that we had before. And I have written the equations in here. They had a horizontal, a linear portion, and a parabola. Whenever the section is non-compact, we're going to find this equation in the code with lambda larger than lambda sub P is more than lambda sub R. R. We're going to find this equation and I'll show you later. Besides bending, we have to check shear. And shear from mechanical solid is BQ or IB. Always is very difficult to compute this Q, but in the code, they have simplified this equation. So I'm going to show it to you later how it's simplified. And in chapter G in the code, we're going to find this equation. So now I'm going to go to the code to chapter F. And this is page 16.1-44. And this is chapter F. And here they give you the design of member for Flexure. Okay. There's a question about what compact means. Right? A compact section is the one that can develop a plastic hinge. So look, if you look at this Y flange is a typical section that we find in the code. Any section that is in the code could have these three stages. Any section of the code, we could have this situation, we have this situation, or the last one. So any section, a Y flange in the code could develop. There are certain sections, the one that cannot develop a plastic hinge. I'm gonna go to the code and show you. I'm gonna come back to this. Go to page 16.147. Go to page 16.147. And if you are on page 16.147, there is a user note. And look, it says in here that all the sections in the code, except section W21 by 48, W14 by 99, W14 by 90, and W12 by 65, W10 by 12. All of these sections are the section. All of them had compact flanges for Fy equal to 50. And all the shape had compact web for Fy smaller than 7. So for compact flanges means that B over 2 times the thickness of the flange is smaller than the limit. So most of the sections have compact flanges, all the sections have compact web. So this is a section. This one is a section in the code that had compact flanges and compact web. But still, it could have this condition. It could only reach this value, it could reach this value, and it could reach this value. When do we have this situation? We say that only the compact section can develop the plastic hinge. So if this section is fully encased in concrete, look, if this section is fully encased in concrete or has shear connector, there's no way that this flange is gonna move. So this flange is not going to move. And here, because it just brace, it's not continuous brace, the flange between the braces could bend. So a section that is compact and is braced continuously, no matter how much load you apply, this will develop. So only compact section can develop a plastic hinge. But even if the section is compact, if it's not properly braced, it's not going to develop a plastic hinge. So the plastic hinge is related to the plastic moment. So the section that I was talking about, depending on this embrace length, it could look only compact section, and they had support or small embrace length can develop the plastic hinge. There are compact sections, the geometry will tell you it's compact, but because of this embrace situation, it will reach a value between M to P and M to R. And that section where this is large, it will never develop the plastic moment. It have a value between M to R and whatever value is in here. So a compact section is the one that can develop a plastic hinge. So in the code, in chapter B, I want you to go to page 16.119. No, compact doesn't mean that it's slender. Look in here. This is a table very similar to the table that we use for the column. However, in here it says the members are subject to flexure. So it's compression because it's a compression flange of the beam, but there's bending in there. And in here it has, in order for this section to be compact, the H over TW has to be smaller than 3.76 square root of E. This is a compact section. Whenever it's larger, that this value is smaller than this value is non-compact. Whenever it's larger than this, it's considered slender. For the flanges, we had in here B over 2 times the thickness of the flange. Look, compact if it's smaller than this value. So most of the sections in the code, the geometry has been selected to be compact section. So all those sections with the proper bracing, they are able to develop a plastic hinge. The only sections that in the code they cannot develop a plastic hinge are the sections given in here. But this is for Fy equal to 50. So someone was saying that chapter F, I'm back on 16.146. Chapter F is the one that deals with bending. And the fifth factor that we use for bending is 0.9. There is something new in here. This is what we used to call the moment gradient. This is what we call the moment gradient in the past, and now they have changed the name. It's the lateral torsional buckling. So this is to be is 12.5 the maximum moment over 2.5 the maximum plus 3 MA, 4 MB, and 3 MC. MA, I want you to underline this absolute because means that in your diagram, if the value is negative, it means that even if the value negative goes as positive. The same in here, MA is the moment at quarter point of the embrace length. M to B is also positive the moment at the middle of the embrace length, and M to C is the moment at 3/4. I'm gonna tell you what it means. Typical beam with uniform load. I'm gonna put an X and X. It means that all of this is L to B. So the lateral support only in here, and lateral support only in here. The moment diagram looks like that. This is the maximum moment. This is gonna be MA. This is also to be MB, and this is gonna be MC. This is L over 4. This is L over 2. And this is 3/4 L. So you have to compute the moment at 1/4 of the embrace length, the moment at 1/2 of the embrace length, and the moment at 3/4 of the embrace length. So it's MA, MB, MC. It happens that in here, MB and M maximum are the same. And this is my cross section. And the bending stresses from mechanic of material MC over I. This is a compression flange. In the compression flange, here the compression flange on top of the beam. This is a compression flange. If you look at the compression flange, and if you look at this formula, the I and the C, they're constant because we have this value in here, the C, and we have this C also. The values are constant. I is the moment inertia about the x-axis, bending about 2. So if I ask you, if I have to compare this point and the beam, this point with this point, which one has higher compressive stresses? This point in here or the one in the middle? Which one has higher? Anybody answer that question? The compressive stresses are MC over I, the middle. Right? So if you look at this situation, if you look at the compression, exactly, the compression flange at this point, minimum stress increases, increases, increases. So there's a gradient of the stresses. So if you compare this case, I'm going to draw only the moment diagram. You compare this case with a moment diagram that looks like this. So in this case, instead of having a parabola, look, instead of having this parabola, we had a uniform. The moment in here is uniform, M all over. And this is MA, MB, and now if we look at the same beam in here, looking at the same beam, we look at the stresses. Look, the same beam. If I look at the stress in here, compared with the stress in here, based on this moment diagram. So if I use this moment diagram and compare the stress at A with the stress in the middle, which one is larger? The one at A or the one in the middle? So look, this is the moment diagram. They are the same. So, and that's the right answer. It means that everywhere and here, they have the same compressive stress. So which one is critical? Which one has more stress? This condition with this moment diagram or this condition with this moment diagram? Which one is highly stressed? This one or this one in here? Top or bottom? The bottom. The bottom, because everywhere we had the maximum stress, everywhere we had the same stress. So you're gonna see that if MA, MB, and MC are the same and the maximum the same, look at this formula. And I'm back on page 16.146. So go to page 16.1. Go to 16.146. Go to that page, F1, chapter F1. Go to that page. And you tell me, if all the moments are the same, what is the value of C sub B? Somebody already answered. If all the moments are the same, look, 1. So C sub B equal to 1 is the critical, is the worst condition. So in the old time, they used to tell us, you can always assume that C sub B is equal to 1 to be on the safe side. For the exam, for the homework, I want you to always compute the value of C sub B for the cases given in the program. For instance, in this case, since the moment is non-uniform, C sub B is going to be larger than 1. So that used to be called the moment gradient because it shows how the moment changed. Today, it's called the lateral torsional backing constant, but it's the same. So go back to the next page, 16.147. And limit state, the same that we talked about before in tension, in compression. Look, symmetric compact, I-shaped member. So this compact means that the flange and the web are compact. So lambda is smaller than lambda sub p. And it has to be bent about the strong axis. We already saw the section that they have problem, but the first equation Remember when I show you this, when the lambda sub p is smaller than lambda sub b is smaller than lambda sub p, the let me go to the top. Look, in the code, they're telling you that you always need to check for bending two values. You have to check yielding and you have to check lateral torsion back. And yielding between parentheses put plastic moment. So the limited state of yielding is when the nominal capacity is equal to the plastic moment equal to Fy times this is the plastic modulus. So when did that happen? They put it in here. When lambda sub b is smaller than lambda sub p, the limited state of lateral torsion backlink does not apply. I'm going to show you again what I had before. This is your beam. This is the embrace length. Whenever the embrace length is smaller than lambda sub p, you're going to be able to develop the plastic hinge. So phi m sub n is equal to phi m sub p. Whenever the embrace length is between L sub p and L sub r, you're going to have a linear equation, lateral torsional pattern. Whenever the embrace length is larger than L sub r, you're going to have also lateral torsional pattern. So I'm back on page 16.147. On this page, if your embrace length is smaller than lambda sub p, you're going to be able to develop the plastic hinge as long as the section is compact. So two conditions. Lambda had to be smaller than lambda sub p for the flanges for the web. And also your embrace length has to be smaller than lambda sub p. We develop the plastic hinge. This is lateral torsional backlink. We're going to see that in a couple of weeks. Right now, we're going to see this type of situation. Whenever we have bending, we have to check bending, shear, and deflection. Look, whenever you embrace length is between L sub P and L sub R, this is lateral torsional backlink. This is C sub B. This is M sub P. Linear equation, M sub P. This is what they also call M sub R, 0.7 FYZ. This is the difference between embrace and L sub P, L sub R and L sub P. They have to be smaller than M sub P. Nothing can be larger than the plastic moment. Nothing can be larger than the plastic moment because if you look at the stress diagram I show you before, nothing can be larger than this value. There's no way. We cannot develop anything larger than the plastic moment. That's why in this equation, they make a point that this could be larger than M sub P because C sub B sometimes is 1.6, sometimes it's 2.2, sometimes it's 2.4. When you multiply C sub B times this value, a lot of times it's going to exceed this value. So nothing can be larger than the plastic moment. And I repeat it again, nothing can be larger because you already saw the stress strain diagram. So this is a good limit. And when lambda sub b is larger than lambda sub r, we have the way we compute this is the critical stress times S sub x. Again, it had to be smaller than M sub p. Why are we using the elastic modulus? Because the behavior is elastic. On the next page, 16.148. Go to page 16.1-48. In this page, they give you equation F2-5. This equation, look at this equation in here, F2-5. L sub P is computed 1.76, the radial gyration on the y-axis times the square root of E of F. I want you to write it here 12 because this is going to give you in inches. And if you do not divide it by 12, you're going to get confused. So divide by 12 because it's going to be in feet. So I want you to divide this by 12. This value has already been computed for you in chapter 3. I will show you to you later. But this value for the standard section, you need to divide this by 12. The built-up section that I used yesterday, the only thing that you have to do is replace the RY in here and the FY, and you can compute it. But this is already computed. This is the L to R value, also has been computed for you in chapter 3. It is a long equation. This equation has changed. This equation in all the codes, all the exams, they used to write it a different way. But the answer is exactly the same. So whenever you look at an all exam and you look at this formula, it had changed. In some of the code, make sure that you have a square in Europe. In some of the code, they drop the 2 by mistake. So if you don't have a square in your code, make sure that you put the square. But I think that's already been corrected in the latest edition. But this also, you need to divide it by 12. Most of these values, they are given in the code in chapter 1. And also, they are given in here. So when the time comes that we have to compute this, I'm gonna tell you how to do it. Next page, 16.149. Go to this page, 16.149, and F3. Remember that in the code, they had already taken care of the web up to Fy equal to 70 because everything in the code goes from 35 to 7. But there are certain conditions and certain situations where we had no non-compact or slender flanges. So the flange can be non-compact, could be slender. And here, the code says something important. No matter what, you have to check lateral torsional buckling. So no matter what, whenever you have a non-compact or slender flange, you also need to check lateral torsional buckling. That was the equation before that has C sub B multiplies M sub P minus parentheses M to P minus M to R. You have to check that. In addition, you have to do the computation, the nominal capacity based on local Berkeley. For non-compact, you can see in here, very similar to the previous equation. Doesn't have the C to B. It had M to P, it had M to R, but instead of the embrace length, it uses the L or the lambda, that is B over 2 times the thickness of the flange, the lambda sub P of the flange, lambda sub R of the flange, and lambda sub P of the flange. And for section with a slender flanges means when lambda is larger than lambda sub R, we use this equation. I'm going to go back to chapter B. On page 16.118. On page 16.118, don't get confused this table with the one for columns. In this table, you have the lambda sub P and the lambda sub R that we use in the previous equation. Look, when B over 2 the thickness of the flange, B over 2 the thickness of the flange is smaller than 0.38, the flange is common. When the value and this value here on the top, this is a lambda. So right you call lambda in there. So when lambda is smaller than lambda sub P, the section is common. When lambda is larger than lambda sub P, but smaller than lambda sub R, the section is non-common. When lambda is larger than lambda sub R, the section is slender. And this is what we get in lambda. I want you to go to chapter 3. And I'm going to finish in 3 minutes. I'm going to go to chapter 3. In chapter 3, you have everything that you need for the design of beams. Bending, as you remember from mechanical solid, bending and flexure are exactly the same. So chapter 4 deal with column, chapter 3 with beam. I'm going to go directly to the end of the chapter, and I want you to go to chapter 3, page 208. Chapter 3, page 208. In this page, you have everything that you always wanted to have. You have to be careful how they use the letters in here. Uniform distributed load, shear diagram, moment diagram. And on this side, you have the reactions, you have the shear, the maximum moment, the moment at any location, especially the maximum deflection, and the deflection at any location. So this is for determinant, and also, look, go to page 3218. Chapter 3, page 218. If you look at this is indeterminate structure. Two spans with this load, it gives you the shear, it gives you the moment, it gives you the location of the maximum moment, it gives you the deflection. So this is going to be a very useful table for this chapter. Now, I want to go to the back or to the from the chapter, I want you to go to page 326. Chapter 3, page 26. This is one of the most important tables in this chapter. And this is for 50. And this is the table for, this is the plastic module ZX. This is also given in chapter 1. But you look at a W21 by 44. Some of you that are familiar with this course, look, there are groups. There's a group in here. You can see that they have groups. This group in here, W21 by 44, W16 by 45. Look at these numbers. The one on the top that is bold face, real dark. Look at this number and tell me which one has the smaller weight. The one at the bottom, the one in the middle, or the one on the top? Anybody? The top, the one on the top. The one on the top is the lightest one because we have 45, 68. In each group, the one on the top, bold face, is the best section because it's the lightest section. So the one on the top, yeah, I know you were looking at it wrong. The one on the top, bold face, dark, is the best section of that group. So what we had in here is amazing. I'm gonna look at value 21 by 44. Plastic modulus. This is phi m sub p, the plastic moment multiplied by 0.9 because it's for LRFD. We had a phi m sub r. This is what we use for the lateral torsion buckling equation. But I told you L sub P is computed in 4.45. So any embrace length up to 4.45 will develop the plastic. Look, we had L sub Y. So any embrace length become between 4.45 and 13, any embrace length will have lateral torsion. They give you this value because we need to compute the flexion. And they give you the shear, the nominal shear capacity. So this is a very good table that we're going to be using. I know I'm out of time, but I want to show you the next thing on page 3-28. And this table I want to look at this group in here. This is the same way that the previous table was organized, but this table is for IX. Right? And in here, they give you IX, another group, IX, IX. The only thing that you get in here is the moment inertia. So I'm going to look at this group in here. If you look at this group, 395, 362, 372, 392, the one on the top, the one that is also bold face, is the lightest section. If you need a moment inertia because the flexion control, you go to the table and let's say that you need this moment inertia, you're going to go and select the one on the top because this is the best section, the lightest one. Let's say that you need this moment of inertia in here. You're going to go to the one on the top of this group because this is the lightest. I'm going to stop here. We're going to continue next week. We had a review on Tuesday. And any time in between that you have questions and anything, just let me know and I'll get online. Now, any questions about anything that I said today? or any concern. Okay. So, if no more questions, I know you have to go to another class and there's a lot of traffic. So remember, I'm available the whole weekend. I'm available tomorrow. Anything that you have, just let me know if you need help. Okay. I'm gonna say so long. Bye.